welcome back. It's day 6 of our series, and today we are tackling what is, no exaggeration, probably the single most transformative idea in the entire history of AI. It is literally the digital brain behind everything from your phone's Face ID all the way to ChatGPT. So let's get into it.
It all started with this one simple but incredibly ambitious question. The idea of looking at the amazing, complex machine that is our own brain and trying to recreate its basic principles using just code and math, well, that's what kicked off the entire AI revolution we're seeing today.
Okay, so to really get how an artificial neural network works, we've got to start with the original blueprint, right? And that's the biological neuron that's firing away inside your own head right now.
So, check this out. On the left, you've got the real deal, the biological neuron. It gets electrical signals, chews on them, and then decides, hey, should I fire off my own signal? Now, on the right is its digital twin. Instead of electricity, it gets numbers. It then multiplies those numbers by something called a weight, which is just a fancy way of saying it decides how important each number is. And finally, an activation function makes the call on whether to pass that info down the line. See? The core idea is exactly the same. Input, process, output.
Look, a single one of these artificial neurons isn't going to change the world on its own. It's just a simple little calculator, really. The real magic, the absolute game changer, is when you connect thousands or even millions of them together in these intricate layers. That's when you get an artificial neural network. And that's when you get a system that can do so much more than calculate. It can actually learn.
So how does this whole thing work? Well, just picture a factory assembly line. Your raw data, say a picture of a cat, gets fed into the input layer. Then it travels through what are called the hidden layers. Now, this is where the magic really happens, as different layers of neurons work together to spot patterns like whiskers, pointy ears, a tail. You get the idea. And finally, the finished product, the network's final answer, like, yep, that's a cat, is delivered by the output layer.
All right, so we've got the structure down. But let's be real. How does this thing go from being just a random jumble of connections to something smart enough to identify that cat in a photo or translate a sentence from one language to another? It all comes down to the learning process. The official technical term for this is backpropagation, which I know sounds a little intimidating. But trust me, the concept behind it is actually beautiful and way more intuitive than it sounds. Honestly, it's a lot like how we learn a new skill, just through a whole lot of practice. This dart-throwing analogy is just perfect for explaining this. Okay, imagine you're learning to play darts. Your first throw is the network making its first guess, its first prediction. You see how far you missed the bullseye? That's the network measuring its error. Then, and this is the really important part, you think backwards. Why did I miss? Was my aim too high? Did I let go too early? That's the network tracing that error all the way back through its layers to figure out which connections messed up. Then what do? You adjust your stance, your aim, and you throw again, hoping to get a little closer. That's the learning loop, right there. So here's the most crucial takeaway of all. We don't sit there and explicitly program the rules into the network. Nobody tells it, okay, a cat has pointy ears, whiskers, and fur. Nope. The intelligence actually emerges on its own through this relentless cycle of trial and error, repeated millions and millions of times with tons of data. The network literally teaches itself. Now, this brings us to a really fascinating bit of history, because while all this feels super modern and cutting edge, the basic idea, it isn't new at all. In fact, it's been kicking around for decades. I mean, look at this. The first mathematical models of neurons were dreamed up all the way back in the 1950s, but they didn't really start changing the world until the 2010s. So what happened? Why was there this massive 60-year gap between the invention and the revolution? Well, it turns out it took a perfect storm of 3 huge things all coming together at just the right moment. First, the internet gave us big data. These networks are hungry, and we finally had enough data to feed them. Second, powerful graphics cards, or GPUs, which were actually made for video games, turned out to be absolute beasts at doing the exact kind of math neural networks need. And finally, some key breakthroughs in the algorithms themselves made the networks way more effective and stable. So just how powerful was this perfect storm? Well, think about a classic problem like recognizing handwritten numbers. A simple neural network, when you power it with all this data and modern hardware, can now hit over 98% accuracy. That's often better than a human can do. And remember, that's just a simple network. And that thought right there brings us to the end of day 6, but it sets the stage perfectly for what's coming next. Because if this is what networks with just a few layers can pull off, what happens when we start adding dozens or even hundreds of layers? Well, that's when you get deep learning. And that, my friends, is when things start to get truly magical. We'll dive into that tomorrow. See you then.